This is exercise 7 from the section 5X quiz. It says find the lump sum deposited that will yield the same total amount as this yearly payment made at the end of each year for 20 years at the given interest rate compounded annually. Now, this lump sum is a clue. When we first talked about the present value of an ordinary annuity, we introduced it as a way of finding out what single payment that was just put into an account and left alone would be equal to an ordinary annuity with certain periodic payments. That's the way we introduced that. So whenever you see that lump sum phrase, even though later on we mostly dealt with present value as a way to figure car payments and house payments or any kind of loan payments, the actual way we first began talking about this idea of present value was talking about this lump sum payment, putting a certain amount in and just leaving it there to be equivalent to an annuity with a certain periodic payment. So whenever you see lump sum, it's kind of a clue that this is a present value problem. So what I'm trying to do is help you out in the beginning, because if you choose the wrong formula, obviously you will be in trouble. So whenever you see that lump sum or putting in an initial amount and comparing it to something with periodic payments, you can bet this is going to be a present value problem. So the present value of an ordinary annuity, there's the formula. You know it. The P stands for present value. As usual, the capital R is the periodic payment. Now, we're still going to have the T for the time in years. So here T is 20, but in general, T is the time in years. And we're going to have a number of, let's see, we're also going to have an interest rate, which in this case is 6%, so little r is 0.06. So again, little r is the annual interest rate. And then little I is really r over m, so we need to know what m is. M is the number of compounding periods per year. And of course, once we know all those things, we can calculate little I and little n. Little I, the interest rate per period, is the annual interest rate divided by the number of compounding periods per year. So in this case, that would be 0.06 divided by, now let's look, M is, it's compounded annually, that's once a year, so M is equal to 1. So you're dividing by 1. So this is one of the cases where M is equal to R. And little n is M times T, which again is 1 times 20. 20 times 1 is 20. So again, whenever M is 1, I is the same as little r, and little n is the same as little t. So we're ready to go now. The present value is the lump sum, what you start with. So we're looking for that. The periodic payment, I guess I didn't say what that was. That's the $2,400. You're putting it in. It says the yearly payment made at the end of each year. That's the capital R. So that's $2,400. And you've got 1 minus the quantity 1 plus little I, which we decided is 0.06. Now there's a negative exponent, so it's minus little n, which we decided was 20. So it's negative 20. And then all of that is divided by 0.06. Now it's just a matter of being careful. So the present value is 2,400 times. Now, as I've said many times, you can leave a lot of this in your calculator, but I'm going to write down some intermediate steps in case you need to go back and check your work for a mistake. So what I'm going to do now is attempt to take this 1 plus 0.06, which I know is 1.06, I can do that in my head, and raise it to the negative 20 power. Now, on this calculator, and on most calculators, you can't directly enter a negative number. So I want it to be a power, though, so I hit the power button. And then instead of entering a negative 20 directly, I enter 20, and then I find a button on the calculator that says plus minus. And on this calculator, it's right there. That just changes the sign of whatever number's in the display. So if I hit plus minus, it turns into a negative 20. So now I'm ready to raise that base of 1.06 to the negative 20 power. So I hit equal. And that is this quantity right here, the 1.06 raised to negative 20 power. You can just leave that number in your calculator and not write it down. I'm writing it down in case someone makes an error and is trying to trace it, and this might help. But when you're solving this problem, you can just leave the number in the calculator. Now, how you proceed from here is essentially up to you. You can store this number you can just write it down and type it back in later, but you can also store this number in memory, and I showed you in an earlier problem how to do that. There's a key on this calculator called MR. That's memory recall, but above that in yellow, which is a shifted key, is MN, and that takes a number and puts it into memory. So you could do shift and hit that MR. That put that number in memory, and then whenever you want it to pop back out, you hit MR, which is the unshifted version of that key, and that number will pop back out. I'm going to do something a little differently. I'm going to take advantage of my knowledge of arithmetic. I know that subtracting is like adding a negative. So what I'm going to do is I realize that I've got this 0.318 whatever in there, but it's not negative. But I know that subtracting is the same as adding a negative. So if I just click this plus minus key, it changes it to a negative, and I can subtract by just adding. So now that I've got it negative, I can just add this 1. That's an understood plus, so it's like plus 1 equal. And I did it without using the memory key. It's totally up to you. You don't have to do it that way. You can just write the number down and enter it back in again. You can use the memory function. But that's the way I like to do it because it's fewer keystrokes. So in any case, however you get to that point, that should be the number, that 0.688195, so it should be the number you have. And I want to divide that by 0.06. And for completeness, I'm going to write down a lot more than you would. Like I said, you probably are not going to write down all this. You just leave the number in your display. But I'm going to write down more than that. So now I'm dividing that number by 0.06. Divided by 0.06 equal. And so I end up with the present value is 2,400 times 11.46992122. So when all is said and done, when I multiply those two numbers together, the number is already in the display, so I just need to multiply it by 2,400. Hit equal. And so I end up with $27,527.81. So that is the present value of that ordinary annuity. And I knew to use that formula because of this key phrase lump sum.